All right, so Unit 5, Part 5, Inference Proportions. Here's our review questions, multiple choice. We've calculated a 95% confidence interval and would prefer our next confidence interval to have a smaller margin of error without losing any confidence. In order to do this, it says change the Z star. No, if you change that, then you change the confidence interval. If it becomes smaller, then my interval becomes wider, so that's not a good choice. This one is take a larger sample, this one's take a smaller sample. To decrease the margin of error without losing any confidence, we always take a larger sample. That answer is B. Number two there says, what is true about a 98% confidence interval for a population proportion based on a given sample? Okay, the first one says we are 98% confident that other sample proportions will be in our interval. No, 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 no. Other people's proportions and intervals and stuff don't fit in ours. We find ours, people find their others. We're not 98% confident about any of that. One is wrong. Number two, it's got that ugly word right there. It says 98% chance. I've told you and told you. No, mark that off. Now, the question is three true? Because the answer might be none. The interval is wider than a 95%. That is absolutely true. 80%, 90%, 95%. My hands keep getting wider. Y'all can't see it, but that's what's happening. Or we could do 80%, 90%, 95%, 98%, 99%. The wider they are, the better. Never, ever, ever find a 100% confidence interval. That's just the top minus the low value. Okay, so the interval is wider. That is 3. 3 only is D. Number 3, we have calculated a confidence interval based on the sample size of 100. Now we want to get a better estimate with a margin of error that is only 1/4 as large. Okay, hopefully we know that our margin of error equals Z star, which isn't going to change, times the square root of P and Q over N. Okay, if we want this to be 1/4 as large, okay, that means we're taking this, whatever this value is over here, we're dividing this by 4. To be able to divide that by 4, we had to take the square root of some number, some N. It was 100. Square root of what number is 4? Well, that's 16. So I go 16 times 100. That answer is going to be E. Okay, number 4, a certain population is bimodal. We want to estimate its mean, so we will collect a sample. Okay, if the population is bimodal, then it says what would be true if we use a large sample rather than a small one. The larger the sample, the more closely it resembles the actual population. So the large sample is 1, yes. The distribution will be more clearly bimodal compared to a small sample. That's true. The sampling distribution of the sample means will be approximately normal. That is always true. You need to make a note somewhere to yourself. Sample means will always be approximately normal. The variability of the sample means will be smaller. The larger the sample, the smaller the variability. The larger the sample, the smaller the variability. So that is also true. So that number 4 is E. It's all of those. Okay, number 5, the manager of an orchard, starting to say orchid, expects 70% of his apples to exceed the weight requirement there. Okay, so this is going to be an equation just like we had up here. My ME is going to be plus or minus, well, I'll write it down here, 0.04 plus or minus. Doesn't really matter on this because we're solving. Can have a negative value. And my Z starts 90%. This is 1.645. And this is the square root of 0.7 times 0.3 over N. And when you work this problem, divide by this. Find this as 0.21 squared. And divide this divided by this, divided into whatever this number is. N is approximately 356. So that answer is D, about 356. Okay, number 6, a p-value indicates. What does it indicate? The probability the null hypothesis is true. No. No. The probability the alternative hypothesis is true. No, that's not what it indicates. The probability the null is true given the observed statistic. No. But the next one, switching this around, does make this true. The probability of the observed statistic given that the null hypothesis is true. We got to have the sample, the observed statistic, to be able to show that we reject or accept the null, reject or fail to reject the null hypothesis compared to evidence that we've gathered by running the test? The answer here is D. Okay, on the flip side, number 7. Okay, you see all these null and alternative hypotheses. The first thing you should do is look and say, nope, that one can't be right. Maybe. Nope, that one can't be right. Nope, that one, maybe. Because these two have equal sign, these do not. With the null hypothesis, A, C, and D cannot be right. So I then see, oh, it wants more than 80%. I'm not even reading the paragraph. It wants more than 80%. More than 80, less than 80. Ding, 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 ding. Here's my answer. The answer number 7 is B. Okay, not wanting to risk poor sales on the new soda flavor. They want to run another taste test, this time requiring a higher approval rating than they had an earlier test. The higher standard of proof will increase the type 2 error. The higher approval rating, okay, lowers the alpha. The smaller the alpha, the greater the risk of a type 2 error. If we drop the approval rating, then we risk these two. But a higher approval rating causes a type 2 error. They might end up failing to reject, and they should have. Okay, number 9. Suppose that manufacturer is testing one of its machines. It's more than 97%, so there's equal here, greater than here. The p-value is 0.122. Compared to alpha, that's large. Compared to 0.05 or 0.1 or anything else, that's still large. Unbeknownst to them, oh, it's a large p-value, so we fail to reject. Okay, if we fail to reject, correctly fail to reject, no, because it's actually producing 99%. They correctly reject, no. They reject the whole, no. They fail to reject these two. But when you fail to reject, and you should have rejected, that is a type 2 error. Fail 2, type 2. Fail 2, type 2. Number 10, which of the following is true about type 1 and type 2 errors? One is not worse than the other, so that's wrong. It all depends on the situation, which is 2. The severity depends on the situation being tested. That's true. And in any given situation, the higher the risk of type 1, the lower the risk of type 2. These two have an inverse relationship. As one increases, the other decreases. It's a negative relationship, if you will. So that answer is 2 and 3. That is E. Number 10 is E. And real quickly, I'm just going to touch on 11. Small sample size, bigger sample size. Which one's most likely to have a wrong answer? Smaller sample size. Smaller the sample size, the more risk of variability from the true proportion. Okay, that's a little bit shorter than the free response. I hope you have a great rest of the day.